Warp speed, Mr. Sulu. It's the kind of command we've only heard in science fiction. Did a team of scientists just bend spacetime using nothing but sparks in a lab? That's right. Not black holes, not neutron stars, electrical sparks. A new experiment claims to have created tiny ripples in the very fabric of space and time, right here on Earth. If it holds up, it could be the very first step toward technologies once thought to be possible only in science fiction. Warp drives, fusion reactors, even medical time control. But is it the real deal? Or just a very flashy illusion? I sat down with Cambridge University's Ben Alanak to explore how this research, powered by lasers, sparks, and Einstein's equations, could be reshaping the future of space travel, and whether it really stands up to scrutiny.
Space-time is the addition of space with time. Time and space don't behave like separate entities. Actually, in physics, we realize they're part of one thing. So you can mix one into the other and so on by going fast and various weird effects like that. But the other thing that happens is that large gravitational fields bend it, warp it, or any gravitational field does, but if it's large, it'll have a large effect. So, for example, the sun warps space and time around it. Time travels at a very slightly different rate in different gravitational fields, and you can describe space as being bent around it as well. So, for example, a light ray, which normally goes in a straight line, will bend around the sun a bit, and you can measure that. That's been measured.
So gravitational waves normally come from massive cosmic events, or black holes, the sun. How can something as small as a spark possibly make them?
Well, the authors claim that because the energy density in a spark coming from two electrical contacts breaking air down is enough to form a small gravitational wave, which they've then detected with lasers, they claim. But it's 400 kilovolts, and it's a sort of little cylinder of something like 2 centimeters long of air. So indeed, I'm skeptical. In fact, if you do back-of-the-envelope calculations, there's nowhere near enough energy to produce a gravitational wave that would be measurable with the equipment that they're using.
So they use these lasers to measure tiny distortions. So how can they actually detect whether the light is being stretched or squeezed?
So what they do is they split a laser beam into two and then recombine it. And that is a very sensitive measuring device. Because light is like a wave, the two waves interfere, but the wavelength is very small, so that you get fringes from the interference, and they observe that those fringes are moving, and they say if you interpret that as being due to the gravitational wave, then they say, well, we've seen moving fringes, we've tried to rule out the other explanations of moving fringes, and therefore this is evidence for gravitational wave detection on the tabletop experiment.
And if space-time really is bending, what could it mean for the future? What are its implications?
They suggest all sorts of possible uses. You could make something like a warp drive, try and use it for propulsion. You could use it to try and change the rate of chemical reactions, which would have a lot of medical and industrial applications and so on.
So what needs to happen in order to prove that space-time really is bending and it's not just a trick from heat, light, or vibrations?
Like I say, they tried to rule out all the other explanations that they could think of, or there's one experimentalist and one author actually. So he has tried to rule out the other explanations. But someone else firstly needs to reproduce the results with their own experiment. I don't know because I'm not an experimentalist, but my suspicion is that there'll be some maybe subtle experimental systematic effect which is producing this movement in the fringes, which has got nothing to do with gravitational waves, but which is to do with other aspects of the experimental setup. The reason I feel that is because there's nowhere near enough energy to produce an observable difference due to bending space-time. The amount of space-time bending you get from an energy density is really tiny. So you need things like black holes colliding, which has colossal amounts of energy in it, in order to be able to observe it.